Hi, welcome to SignalPad. In this episode, I have another tutorial for you guys, and I've been wanting to make this video for quite some time, and I'm really excited about it. We're going to talk about lock-in amplifiers. Now, the one I have here is an SR530 lock-in amplifier. When I was an undergraduate student, the very first year I joined electrical engineering, I was a summer student in the optics lab, and I was doing some experiments there, and there was a lock-in amplifier I was using, and at the time, it was working, it was doing what I wanted to do, but I had no idea how it was working. It was like magic. It was on a couple of years later where I actually learned how it works, and I was amazed at the elegance and the simplicity of its operation. That's what we're going to talk about today. Now, what I really wanted to do was to show you a state-of-the-art lock-in amplifier, and Stanford Research is one of the leaders in making lock-in amplifiers, and this is a pretty old unit. So I called them and I said, hey, I make these YouTube videos, I have this channel, I have these viewers, and I want to make a tutorial showcasing your latest instrument. And they told me that, well, they already are the leaders in making lock-in amplifiers and they already have enough publicity, and so thanks but no thanks. They don't want to have any additional publicity, so they didn't want to send me a unit. So I went ahead and I just bought a much older one that I could afford, and I can afford that thanks to my Patreon supporters. It's because of you that I managed to be able to buy this unit and make this tutorial that I hope you enjoy. Well, I'm a little bit disappointed in Stanford Research Systems because I thought that they would have some value in the education it brings the community, but what can you do? It's a business after all. So we're going to do it with this SR530, which is a significantly older, simpler unit, but it will definitely demonstrate the point. So before we do any of that, I need to tell you how this actually works and what is the principle of operation behind it and a block diagram of what is inside of it. And we're also going to take a look at what's going on. And I have a couple of cool experiments at the end that we're going to take a look at. So without waiting, let's talk about the operation and the principle of how it works. So why should we care about lock-in amplifiers at all? Well, imagine that there is a signal that you want to measure, and that signal happens to be this signal right here. Now it's going to be buried within the noise of your detector, because any detector that you're going to use to pick up any signal, that signal could come from an electromagnetic field, it could be a chemical reaction, it could be anything. Your detector is going to have some noise, and that noise is typically white. So let's say that noise is right here. So if your signal is very small, it can get easily buried in the integrated noise of your detector as well as your instrument. For example, the detector noise can be so wide and can be so high that the peak-to-peak value or the RMS value of the noise can be much higher than the signal of interest, so you couldn't distinguish them from one another. And this doesn't even include noise coming from interference and other things that could be present in your system. So how do we solve this problem? How do I get my signal out of my noise? Well, one way to do it would be to filter it. Let's say I put a filter right around my signal to get rid of as much of the noise as possible. Well, in order for this to be effective, the quality factor of this filter would have to be in the thousands or even in the tens of thousands. And then maybe you can get enough SNR to bring your signal out of the noise. Now immediately you can see that building such a filter is quite impractical, because to have a filter of 10,000 Q is already hard enough, and then you'd have to make sure that the sender frequency lines up with the signal you're trying to measure, making it even more difficult. And that doesn't even solve the problem of some of the other noises of source that are there from your instrument. So that's going to be a problem right off the bat. So we can't do this. Let's think of a different way to do it. It would work if you could build it, but of course building it is a problem. So now imagine if there was some device called a lock-in amplifier, and it wants to measure the signal that is of our interest. Now it's going to have system noise, it's going to have background noise, this could be a noise coming from electromagnetic radiation, it could be, let's say, stray light in your optical measurement, or a whole bunch of other things that are coming together. Now we want to measure this signal in the lock-in amplifier. So let's take a step and do something kind of crazy. Let's do some arithmetic on our signal and see what happens. So imagine that you have this system instead, where your input signal is defined by a sinusoid like this, Vx sine of omega st plus alpha, which is an arbitrary phase. So this is a frequency of omega s associated with a signal of interest, Vs of t. Now imagine that there is also a reference signal, and that reference signal is Vr of sine of omega rt. So it has a different frequency, omega r, and it has a reference phase of 0. It doesn't matter, that's why it doesn't have an alpha term. You could add it if you want to, but it doesn't matter. What only matters is that they're in different phases. So now you have two sinusoids with two different frequencies. Now imagine that your lock-in amplifier multiplies these together, which is to say it mixes them together. What would you get as a result of that? Well, this is pure math. If you multiply two sinusoids with two different frequencies, well, you're going to get this equation down here. And this equation is nothing more than two cosines with a sum and the difference of the frequencies of those two sinusoids. This is classic mixer equation, very straightforward. So here's our equation, the two mixed together. Great, what can we do with this? Well, imagine now that you could take this and you could integrate it over many cycles of the sinusoids, or in this case the two cosines. What would happen in that case? Well, any sinusoidal signal that you integrate over many cycles is going to be zero, because the positive and the negative cycles of the sinusoids are going to cancel each other out. So if I were to integrate this, oops, I lost it, where did it go? If I were to integrate this over many cycles, it's just all going to disappear. It's going to collapse to zero. That's not very useful, except for one crucial point. If the frequency omega s and the frequency omega r happen to be the same, then these two terms go away, which means you're left with cosine of a constant, alpha. And that alpha is not a time-dependent parameter, and as a result, we're going to be preserved in the integration. This term is going to go away. Let's forget about this term, and you're going to have a constant multiplied by another constant, which means that if I could somehow get omega s and omega r to be exactly the same, I would cancel out every frequency in the system except for where those two frequencies are the same. And this is the genius part of a lock-in amplifier. The system inherently will reject every frequency that is not the exact frequency omega s of your signal of interest. And that's how it works. So if I could somehow create this and feed these two together to a lock-in amplifier and let the lock-in amplifier integrate the signal, it will completely bring it out of the noise. And what I will end up with is that the effective bandwidth that I'm looking at can be so small, it can be in the tens of millihertz, and it can completely filter out everything outside of this frequency completely out, and I will only be left with this ultra narrow band in the middle where my signal resides. And that's how it works. That's the magic of doing this equation and figuring out, realizing that the integration works if you were to match omega s and omega r. Now this is very important that these two signals have exactly the same frequency, which is why here in this diagram the modulation source is shown to multiply with the signal and go to the lock-in amplifier at the same time. If you don't do that, then you get nothing. So now, having said that, this is pretty interesting, but there is one little problem here, is that now we have a cosine of alpha, and for some values of alpha, the cosine of alpha will be zero. So how are we going to deal with that situation? Well, in the case where alpha is 90 degrees, let's say, you're going to have a problem. But if you were to build a lock-in amplifier that had two mixers in it, where one mixer was operating on alpha and the other mixer was operating on alpha plus 90 degrees, then now you would have two vectors. And those two vectors would always give you the angle of alpha, and you could calculate exactly the terms that would come out of those two equations, and you would always have a signal. So this is exactly what the two-channel lock-in amplifier that I have does. It has two mixers in it, and one of them is operating on a 90 degree, like an IQ signal, in order to never collapse this term to zero and be able to give you the exact angle between the signals coming in. So what does that block diagram look like? Here it is, and we can go through it and see how it works very quickly. So the input obviously has a differential voltage amplifier. It also has a current input, and the current input goes to a current to voltage converter, which is a transient impedance amplifier, and you can select which of these two you want to use. And we're going to use both of these in our two different experiments. And then there's some zero and some line frequency notch filters that you can enable. And you can imagine that this is extremely helpful because it will eliminate the line frequency that's coming in. So if your system is running at 50 hertz or 60 hertz, you could put a notch filter right at that frequency in order to take out any line signal feeding into your experiment. So this can be pretty helpful, some pre-filtering before anything is done on the signal. And there is some auto-tracking bandpass filter that tracks the signal to further clean it out to really create the front end to be as low noise as possible. So you can enable all of these things. And then there is some high gain amplifier, and then there's an output at the back so you can monitor the signal and make sure it is what you expected. And then the mixers will begin. Here's our first mixer, here's our second mixer, and here's our reference frequency input. So the reference frequency input goes through some PLL, some phase shifter, and then goes through our first mixer, and then it goes through a 90-degree phase shift, which is exactly what I was talking about, and goes through another quadrature PLL, and voila, you get two mixers simultaneously operating on the signal on two different 90-degree separated waveforms coming from the input reference. And then you can put them through low pass filter, which is the integration I was talking about, and even further low pass filters, even more filtering going on, and then you get R cosine of theta and R sine of theta, which are the two 90-degree angle signals coming out, and you can get the amplitude of those two and therefore get exactly the signal you're looking for. So what that would mean is that if I go over here, I will have this term plus one with a 90-degree and one without a 90-degree, which would be the equivalent of a sine and a cosine, and I can find out exactly what the relative phase between my Vs of t and Vr of t is, and also preserve the Vx and Vr of the signal, which is the RMS signal of the signal coming in. So it all really works very nicely together, and then you can get these two signals out. And at the same time, those two signals also go to some analog multipliers and a 12-bit A to D converter and a microprocessor system. And this microprocessor system, oh, I don't want that. And this microprocessor system is going to take these two signals and it's going to process them mathematically, digitize them and process them mathematically, and figure out the angle between the two of them by doing some basic arithmetic. And then it can tell you what is the exact phase digitally. So this has a digital readout of everything that's happening, and you can see a whole bunch of digital controls that can further be done on the signal after it's digitized. So this is the block diagram of our SR530 two-channel lock-in amplifier that we're going to be using for our experiments. Now I know I went over this fairly quickly. There is tons and tons of more stuff to consider. For example, what frequency do you choose to do this at? How do I choose my reference frequency? How do I modulate my signal that is coherent with the reference frequency? There's so many things to consider. Very high frequencies are problematic because capacitance in the circuit start to kick in. Very low frequencies are problematic because you'd be in the 1/f noise region of your detectors or the front end of the instrument. So there's so much to worry about, but hopefully this excites you to go and look deeper and figure out some of these things on your own. There's lots of material available on the internet, but hopefully this gets the point across. So the next thing is, let's take a quick look inside the SR530 and then we'll do our pretty cool experiments. Let's go. So let's take a very quick look inside this unit. I'm not going to go into too much detail, just want to give you a general idea of what it looks like inside. This is all through-hole technology. This is pretty old, from the 90s and so. So now the input signals over there, both for the current and the voltage input, go under this cage. And that's where we will have our transimpedance amplifier, our front-end amplifier, as well as our filters are going to be all underneath there. There are some holes for some potentiometers, perhaps for some offset and so on for the calibration. Now, I'm not going to take that cage off because I don't want to get any debris on the PCB. That particular portion of the circuit deals with very small voltages and very small currents, so you don't want to disturb it in any way so that the unit doesn't come out of calibration. Other than that, there's not going to be anything unusual under there, just a base of bunch of discrete components again. At the top left, our transformer comes in. We have a bridge rectifier, a lot of capacitors there, power transistors or voltage regulators, creating a very nice solid power supply for the entire instrument. At the top we have a backup battery, Zilog processor, as well as EEPROM and some memory, and our A to D converter will be somewhere around here, where we have all the computation done and controlling all the front end LEDs, and as well as doing the computation I just talked about for calculating the angle and the voltage and so on. So it doesn't need a lot of computation power, but it does have some over there. And you can see that this PCB at the back is enormous, labeled SR500, so they're probably using the same PCB for the single channel and dual channel, and that can be kind of verified by this PCB here. It looks like they only changed this. And this PCB, I have to say, sitting here in two sockets, kind of loose over there. Doesn't really, it's only held by this little bracket over here, which is quite low, so there is nothing really holding this in place. I'm a little bit surprised at that. And the two signals from there go to the R sine of theta and X cosine of theta, and those are the two signals coming from the mixer. So it looks like that portion of the circuit is going to house our dual channel. Other than that, really straightforward, nothing unusual going on. We have the back of the two analog meters there. The front panel control is another PCB in the front. Really nice, clean design. This is what Stanford research designs look like back then, and they're obviously going to be much more modern these days. But they do tend to stick to their old design for quite a long time. They're known for that. So yeah, other than that, looks pretty good. I'm very excited to get to our experiment. So let me start building some of those, and I'll tell you how they work. So now that you've seen the block diagram and the internal construction as well as the theory of operation, we can take a look at some of the features of this unit. So first of all, this unit has input A and B, which are voltage inputs, and I, which is a current input, and I showed you in the block diagram, transimpedance amplifier in the front of the current input, 10 to the 6 volt per amp is the gain of that. Here's the band pass filter selection, so you can turn various ones on and off. And here is the sensitivity, which is the dynamic range front end and what is the maximum voltage that it can handle or maximum current that it can handle. So that you can set over here. And the right side, we have the input, which is going to be the reference input, and the reference frequency will be displayed over here. The time constant, which is the integration time constant, both the pre and the post can be selected here. The phase of the reference can be modified here, and the phase, of course, by modifying the phase, you're going to change the value of the R cosine of alpha and R sine of alpha. And we're not going to play around with this too much because we have a 2-channel lock-in amplifier, so we have both of the information of the quadrants available to us. We have 2 outputs over here, and the output X and output Y, which is the R cosine of theta and R sine of theta, are both available to us. We can change the display to show XY, offsets, the magnitude and the phase, and a whole bunch of other things. Pretty awesome stuff. Our channel 1, channel 2 meters there, and of course the digital value being selected over here. And a bunch of other things like expanding the range and the dynamic expansion and so on. I'm not going to go into too much detail, but this is a very nice, very classic architecture for a lock-in amplifier. Very famous unit. Too bad we don't have the latest one, but anyway, this is going to be just fine. So now that you know pretty much everything that to get you started, I hope, let me show you the very first experiment that I have put together. I think you're going to like it. And here's the setup for our first experiment. And in the first experiment, we're going to measure the speed of sound. That sounds a little bit unusual. How would we use these instruments to measure the speed of sound? Well, if you think about it, all we need to do is to measure the wavelength of sound, because we can make some assumption about the atmospheric conditions here in my lab, and from that we can compute the speed of sound. So how do we measure the wavelength? Well, we know how sound propagates through the atmosphere, and we know that if we have the phase information of sound as it is traveling through the air, we should be able to then from that measure the wavelength of sound and then go back to the speed of sound. So how do we do that? Well, the SR530, as I explained extensively, is a 2-channel lock-in amplifier, and because it's a 2-channel lock-in amplifier and because it has 2 mixers, we can do phase sensitive measurements, and we can get exact phase information that's coming into the instrument by using the 2 mixers. So what I've done here is that I've taken output X and output Y, which are the 2 outputs from the mixers, and I'm connecting them to channel 1 and channel 7 of the Tektronix MSO5 series oscilloscope. So I can monitor the voltage between these two and view them on the display. So that's the first thing. Second thing is that I'm using the Stanford Research Model DS345, which I repaired in one of the previous videos. I'm using that as my reference synthesizer. I'm taking the sync output and I'm connecting it to the input of the lock-in amplifier. So right now I'm set to 20 kilohertz, and you can see over here on this display that the lock-in amplifier is locked to my Stanford Research synthesizer, and it is detecting the correct frequency coming in. So everything is nice, everything is locked together. Now for the output of the synthesizer, I'm taking the output over here and I'm connecting it to this speaker over here. And then I have another speaker at the top, and I'm taking the output of that speaker and I'm connecting it to the input of the lock-in amplifier. Now, as you know, the way the speaker works is that there's a coil inside a magnetic field, and as you put current through that coil will vibrate and it will move air molecules around, create pressure, and that pressure propagates through a sound, and we will be able to hear it. And now, as a result of that, if you think about it, a speaker is also a microphone. It can also capture, and it can absorb sound waves coming towards it. Those sound waves move the diaphragm up and down, they move the coil, and then they will induce some current and some voltage to be generated. So normally speakers don't make very good microphones, but here for simplicity I'm using an identical speaker at the bottom and an identical speaker at the top so that I can measure the signal this way. It means that a signal comes over here, electrical signal comes over here, goes to the first speaker, becomes sound waves, gets propagated upwards, gets picked up by this speaker, and then it goes all the way back to the input of the Lockin amplifier. So sound generated by the bottom speaker induces a current in the top speaker. So now how does the phase work out in all of this? Well, the synthesizer at the bottom has a very stable phase. So its phase is not moving, it's constant. And even if it were moving, it wouldn't matter because we have a sink connected to the reference input of the Lockin amplifier. So for simplicity, and it's fairly accurate to say that the phase of the bottom synthesizer here is fixed, and therefore the SR530 is locked to this with the reference input. So these guys are locked together. And the phase that's coming out to the bottom speaker, when it propagates through the air, there is going to be some delay, and that delay is a phase difference, which means that the speaker at the top is going to catch a different phase of the signal than is what is coming out of the bottom speaker. So the top speaker and the bottom speaker are looking at exactly the same frequency, but at a different phase. So the top one is going to have a phase difference. And so what does that phase difference depend on? Well, everything in this setup is constant. The length of the cables don't move. But I can change the relative distance between the top speaker and the bottom speaker in this apparatus. So I can move this top speaker up and down. And if I move it up and down, I'm going to change the delay, and therefore I'm going to change the phase between the two speakers. And that's the key in this measurement. So by looking at the output X and looking at the output Y, I will be able to get the exact phase, relative phase between the signal from the bottom and the top speaker. And that's exactly what I'm looking for. I'm looking for catching 360-degree phase change. So I will look at the two outputs of these two signals, and I will look for 360-degree phase change as I am changing the distance between these two speakers. And since this is in a nice apparatus, I will have a very repeatable measurement. So let's zoom in here to make sure we really understand what's going on this right setup and how that phase difference translates to an electrical phase difference, which then can be measured by our oscilloscope as well as the Lockin amplifier. So here's our setup here, and as I explained, sound is coming out of the bottom speaker, being caught by the top speaker, and the distance that I'm interested in is this. Now I can move this distance up and down by moving this knob over here. So this is very simple. This is from my microscope setup actually. And I can then take a ruler, and I can put a ruler right over here and make a reference distance measurement, and then make another measurement once I have accomplished 360-degree phase shift. And here I'm using centimeters because I'm not insane. And from that, we can calculate the exact wavelength. So I can make a nice starting point, and then I can increase the phase up here, and I can then measure again. And by looking at the difference, I can find out exactly what the wavelength is. And the easiest thing to do would be to increase the distance until we see 360 degree of phase change. That would be the easiest to measure, and then from that would be exactly one wavelength, and that's our distance. So it sounds pretty straightforward. So let's take a look at, see what the Tektronix MSO is doing, and then we will be able to do our measurement. And here is the MSO 5 series, and I'm really happy with this scope. I've been playing around with it quite some time. It's really a nice instrument. And so let's go and take a look here. So channel 1, as I said, connected to the X output, and channel 7 connected to the Y output. I'm just choosing channel 1 and 7 because they're easier to connect. And of course, you can do anything with this data with the Tektronix 5 series. It's not a problem. So what I'm doing is I'm showing the two signals down here. And you can see there's some tiny changes as I move around. And the reason is because sound is also being reflected off of me and off of the environment. And there's going to be some perturbation in the signal because of the secondary reflections of sound. So let's look at here. I'm also plotting X versus Y. In this case, I'm plotting channel 1 versus channel 7. And you can see it's a dot, and that dot isn't really moving around too much. It means that the signal is stable. Now, if I take the origin and I draw a line to that, that would give us the relative phase that the two mixers are measuring. So as the phase is changing, you would expect this to go in a circle because you're changing the phase of the signal, so the two signals coming out are going to rotate in a circle. But it's not going to be a perfect circle, and there are multiple reasons why it's not going to be perfect. First of all, if you look at the distance, the physical distance between the horizontal divisions and the vertical divisions, they're not the same. So these are rectangles and they're not squares. So even if the signal was perfectly on a unit circle, you would not get a circle. You would get an ellipse, not an eclipse. I've been thinking about the eclipse too much. So it's an ellipse that you're going to get over here. So that's not going to be a circle anyway. But there's other reasons. Other reasons is because, as I said, there's secondary reflections coming and being caught by the top speaker. So that's going to be limiting how perfect that's going to look like. There's another reason is because as I change the distance between the two speakers, the received signal strength in the top speaker is going to go down because we know that the signal attenuates as a square of the distance between the 2 points, and therefore the signal is going to get weaker, so this point wants to move closer to the origin. Now, how do I know I'm even measuring the sound that's actually there? How do I know this is not just gibberish? Well, let's take a look and see if that's the case. Well, what is an easy way to do it? Well, let's block the sound. How can I block it? Well, I'm going to use something heavy, and I think the heaviest thing that I have around here right now is my phone. So this is a pretty dense piece of metal and glass, so I should be able to block the sound fairly well. So I'm going to move it between the 2 points. Now, what do we expect to see when I do that? Well, these two have to, this point has to move to the origin, meaning the signal would have to go to a 0 if it is changing its magnitude, its strength, which is what I'm doing by blocking the sound. Let's try that out. And you can see, and it comes back to around 0. If I remove that, it will then come back, which means I am 100% measuring the signal of interest. This is not some gibberish, and I can repeat this is very repeatable, and so on. Now, a couple of other things I want to point out is the choice of frequency here. So I am using 20 megahertz, so 20 kilohertz. Now, why am I using 20 kilohertz? Well, first of all, I have to be within the frequency operation of a normal speaker, because the speaker is supposed to be able to pick up that signal. Now, at the same time, if I were to choose, let's say, 1 kilohertz, or 2 kilohertz or 3 kilohertz, it would be extremely annoying because it's going to make a tone and it's going to drive me nuts. So I'm using 20 kilohertz. Now, the disadvantage of using 20 kilohertz here is that these speakers aren't really designed to put out 20 kilohertz because you really can't hear that. So the gain of it is going to be much, much lower than it would be doing in the frequency range that they're designed to operate. But that's okay. We're using a lock-in amplifier. The signal can be very small, and we should still be able to pick it up without any issues at all. So I'm quite happy with that. I have no problem with that part of the frequency choice. And I'm putting a lot of signal into it. I'm putting 10 volt peak-to-peak into it, so because the signal, again, is quite small. And at the same time, let's take a look and see how I've set up the Lockin Amplifier. So the Lockin Amplifier is set up quite simply. I have all my front-end filters are turned on. This is on a 200 microvolt sensitivity range, so it's quite low because the signal is very small. And I also have a 1 second post-processing, time constant on the Lockin Amplifier. Other than that, really, really quite straightforward, nothing unusual there. So now we can go ahead and do some actual measurement and see if it works. Oh no, one other thing I wanted to demonstrate was if changing the distance between those two actually moves this point. So let's take a look. I'm going to rotate and take a look, have an eye on this point here, and check it out. It does indeed move in what appears to be a somewhat circular path. You can keep going, and it's going to continue, and it's going to start to come down, and going to try and make an ellipse there. So you can see it is working, which is really quite amazing. If we think about what it is that we're trying to measure and how easy it is to demonstrate something that is, in the face of it, it's quite complicated, really, what's happening in the background. So let's go ahead and do this measurement carefully now, and I'm going to focus over here, and I'm going to make a reference measurement, and then we can go from there. All right, here's my reference measurement, and if you look carefully over here, I am right at the 12 centimeter mark. So this is my reference point. I'm measuring it with respect to this point right here. So we're at 12 centimeters, and I'm going to increase the distance until we make 360-degree rotation on the oscilloscope, and then we're going to go back and remeasure and see how much we traveled, and then from that compute to see if we get the correct speed of sound. That should be pretty cool. Okay, let's do our measurement. Now, the very first thing I'm going to do is I'm going to make this an infinite persistence, because that way we can see the circle travel and we can have a better idea. So let's go ahead and reduce the distance between the two speakers and see how this dot travels. Here we go. And it should start moving. And there it is. So we are changing the phase between the two speakers. There's a signal between the two speakers. And you can see how at the bottom here, these are filling the screen. I'm going to continue until we have a good 360-degree phase shift. I'm going to keep going, keep going. It's nice. It's not too bad. Now, obviously, they're not going to reach each other in exactly the same place because the signal strength is going to be different. But all we care about is reaching the same point on the x-axis. And I would say this is pretty good. Look at that. That's 360 degrees. And you can see the difference between these 2 points up here will be the difference in the signal strength. It's not actually as bad as I thought. It's a nice ellipse there. So let's go ahead and now zoom back in and see exactly what is the new distance between the two speakers. And from that, let's see if we can compute the speed of sound correctly. So let's see what we have here as our new distance. Let me see if I can get a focus. There we go. So it looks like we are now sitting at about 10.3 centimeters. So given that we started from 12, that's a displacement of 1.7 centimeters, about 17 millimeters is how much I moved to achieve 360 degrees of phase measurement. But is that correct? Well, we'll have to do a computation to find out if that makes sense. So let's see, our frequency was 20 kilohertz, so 20 exponent 3. The distance that we measured was about 17 millimeters, so 17 exponent minus 3. And the speed of sound is 340 meters per second. And that is really, really, really close. In air at 20 degrees Celsius, the speed of sound is 343 meters per second. So we are really close to that measurement. That's really amazing, isn't it? I mean, all I did was set up a lock-in amplifier, 2 speakers, and some measurement to measure the values of those 2 signals, and when they became equal again, I took the difference in the distance. So in principle, it's a really simple measurement, and it of course demonstrates the phase measurement capability of any lock-in amplifier really, and having a 2-channel lock-in amplifier to allow you to do this measurement. So I hope you like this one. So this demonstrates phase measurements and so on, but for our next experiment, we're going to take a look at measuring exceptionally small signals, which is a whole other challenge in itself. This is a device for our next measurement. So what I have here on the left is nothing more than a light emitting diode. This is a red LED. So if I give it some current, it's going to produce a light in the red spectrum. It's not going to be a very precise light. It's not a laser diode. It's just an LED. It's going to have quite a wide line width, but nonetheless, it's going to be around 650 nanometer light coming out of it. And this has to do with the composition of the semiconductor material used to generate that particular wavelength, the band gap of the material, and so on. But it also will do the opposite. If I were to shine light on it, it's going to produce some current. Some photons are going to be converted to electrons, and that's going to produce a current in it. And that current is going to depend on the intensity of the light, but it's also going to depend on the wavelength of the light. Again, because of the semiconductor composition, when this LED behaves like a photovoltaic cell, the photodetector's responsivity to the wavelength of the light is very important. Now, if I wanted to find out what is the sensitivity of this particular LED to blue light, that would be a very difficult measurement to make for a few reasons. First of all, this LED's casing, the plastic casing, is red. So which means that any blue light is going to get inherently quite a bit filtered just by the casing of this LED before it even hits the semiconductor material. And then on top of that, whatever responsivity that semiconductor material has to blue light is going to be an additional challenge on top of the measurement. It's going to be a very, very low responsivity to blue light. So having said that, then how do we make this measurement? Well, there's actually even more complications. Because the ambient light from the room itself is made of many different wavelengths, so if I were to cast a shadow on it, the current is going to change. So it makes it even harder for me to find out what is this responsivity to a particular wavelength of light. And you would have to enclose it in a very fancy case and make sure there's no light, and make sure there's no reflections of the light, and there's so many other precautions you would have to take just to make sure that optically you're protected and you can do measurement at a single wavelength reliably. And then on top of that, you're going to have the noise from the measurement itself. Because you have such a small signal you're trying to measure, source noises, as I explained before, are going to swamp your measurement. Well, the first thing we're going to do is we're going to use this laser diode. This is a blue laser diode, a wavelength around 402 nanometers or so. It's quite close to ultraviolet actually. And we're going to shine that laser into here. So the first thing we're going to do is just hook it up to a multimeter. Now I'm going to hook it up to a Keithley DMM7510, and I'll show you this, basically one of the world's best multimeters. So we have one of the best instruments we can to measure the current coming out of it. And we'll see how difficult it is to catch that current. And especially if I want to find out what happens as I reduce the intensity of the light, and how much I can reduce the intensity and see the linear relationship between light intensity and responsivity. So all of this have to be set up first. So let's do the very basic thing and just see what happens if I were to do this using a regular multimeter, or I should say a very good multimeter, and see what happens, and then we'll build a setup from there. Alright, here is our setup. So what I've done is I've connected the laser diode to an XYZ manipulator and the LED to another manipulator. This allows me to line them up very easily and precisely. And the light from the diode is going to therefore directly shine on our LED and induce some current. Now, as far as measurement instrument is concerned, I'm using two Keithley instruments. As I mentioned, I'm using the Keithley DMM 7510 at the very top to measure the current, and I'm using the power supply at the bottom, which is another Keithley 2280S, which is a really nice power supply, one of my favorite in the lab for sure. And that's going to provide the current to turn on the laser diode. So I'm going to turn the laser diode on with a 50 milliamp current. And that's roughly around where it's supposed to be operating. So as you can see, without me turning the laser diode on, I'm already measuring some current. So this is in the microamp range, so we are dealing with 0.000195 microamp. So there's 3 zeros there that takes you from microamp to nanoamp, and the last will be picoamp. So we are looking at that just under 200 picoamp. And 200 picoamp is a very small current, and we have no problem measuring it with the DMM 7510 because of its low noise and high resolution. But nonetheless, this is ambient dependent. So if I shake my hand around it, you can see I'm just moving my hand around and blocking the light and creating some shadows, and that number is going to be all over the place. I can turn the lights in the lab off. If I turn them completely off, and you can see that drops significantly. Now we are in the tens of picoamp. And the reason there is still some current is because there is stray light in the lab. My monitor is on, and some work light is on. So there's still some light coming to the LED. And if I put my hand on the LED around it, I'm not really able to block it that much more than I'm blocking it now. So having said that, I can turn the lights back on again. So that's going to be stray measurement, which is not good. And let me go ahead and turn the laser diode on. Here we go. Here's the laser diode on. You can see 49.5 milliamp being put into it at around 5.5 volts, and the number is now much larger, 856 picoamp. And that's the current induced because of our laser diode. And here it is. You can see there's the laser diode there. If I block it, you can see that the light is there, definitely being shining on top of our red LED. So if I go back to the measurement again, and you take a look, again, if I shake my hand and move my hand around and block the ambient light, I'm indeed going to make some problems in the measurement. And this is not just because of light. Also, EM being present at different frequencies, being picked up by the wires themselves, are going to interfere with such a sensitive measurement. So this makes it very difficult to do this measurement. Let me turn the lights back off again. There you go, light off. You can see the current drops. Light back on, comes back. And if I go into the plotting capabilities over here, and let me clear the buffer completely and do an auto scale on everything. Let me push that button there if I can get it. Come on, there we go. There it is. So now you can see if I move my hand around, that the measurement is going to definitely be all over the place. Turn the lights off. You can see it jumps there, turn the light back on, jumps back up. So you could get some measurements, but there's a limit. So for example, let me turn the current down to the photodetector, to the laser diode, and see how low we can go where we can still reliably make a measurement before we're in the noise of the ambient. So let's go ahead and do that. So right now we're looking at 50 milliamp. Let me reduce it to 20 milliamp. So now at 20 milliamp, the laser is on, but we're basically in the noise of the measurement. I mean, if I block the light with my hand, which I'm doing right now, I get a tiny bit of difference, but really not that much. And it's very difficult to make a reliable measurement like this. And if I go even lower than 20 milliamp, then it's going to be completely buried in the noise. So this is not going to work. This amount, by the way, the light is still on. You can see a very faint light there. So the laser diode is still definitely working. So let's now try to do exactly the same thing, but measure using the Lockin Amplifier. Now, Lockin Amplifier needs a reference and needs the signal to be modulated. So how do we do that? Well, we can use a chopper. Let me show you how that looks like. And here is our new setup up and running. So I'm going to have to go through each individual component of the setup to describe exactly what's going on, because there's a lot of things happening here, and I think it's pretty interesting. So let's take a look at our chopper. So the chopper is this box over here combined with this motor. This is a Stanford research model SR530. It's one of the most famous choppers I think ever made in the industry. Everybody's used one of these at some point, especially if you're in this field of study. So now let's take a look at what's going on. Let me turn the chopper off. It's going to become much more clear when it's turned off. So the chopper controls this motor, and this motor has a disc on it. And this disc has a particular number of holes in it. So as this disc rotates, and there's a light going through it from this laser diode, for example, it's going to chop that light. And you see, if I hold my hand over here, when I rotate this, you can see that it is chopping the light. Which means that if I rotate this at a known speed, I can modulate the light at that exact frequency. And that's exactly what's going on here. You can buy different discs with a different number of holes in it for different purposes, and this disc that I have here has quite periodic number of holes on it. So if I go and turn this chopper on, the chopper is being controlled by this. There is some photo set detector interrupters there, so as the chopper goes in front of those, it can measure the exact frequency of rotation, the RPM, and it's going to use that in a negative feedback system to stabilize the motor and keep it at exactly the desired frequency. And right now I have set the frequency to about 980, 930 hertz or so, which is good enough for our purposes because the LED can react to that frequency without any issues. It's very important not to chop the light at frequencies where your detector simply cannot support, otherwise you'll get nothing out of it. So this is another issue which I talked earlier in the video about. So the light is not being chopped right now by the chopper, and the output of the frequency of the chopper can then be used to feed into the input of the Lockin amplifier, and this is how the Lockin amplifier then becomes phase and frequency locked to the light that's being chopped going through the chopper. So this is how this system is now put together. This means that because the light is being chopped at a known frequency, all other frequencies outside of the frequency that's being chopped are going to get completely rejected. So the system becomes completely insensitive to ambient variation. And of course, as I again mentioned earlier in the video, it's going to get filtering all the noise outside of the band that is not exactly the frequency where this chopping is happening. Now remember, it doesn't matter that this changes a little bit because the Lockin amplifier is going to track that change, so we're still going to remain locked in the total system structure. So pretty straightforward. Let's take a look again from far away so we can make sure all the components are in place. And here you go. I'm not sure if this is in focus or not, but let me make sure we're focusing up here in the front. There it is, the input to the Lockin amplifiers coming from the chopper controller, and the output of the LED is going directly to the current input of the Lockin amplifier. So I'm not using the voltage input, I'm using the current input. And that's important because I want to measure the flow of electrons in the current format. Now, the input of the Lockin amplifier on the current input is a transimpedance amplifier. It has a gain of 10 mega ohm, so it's the transimpedance of 10 mega ohm, and it's 10 to the 6 volts per amps. And that means that you're going to have to take into account, when you read a number over here, you have to take into account that you have a gain of 10 to the 6 volts per amps from the front end. As a result of the transimpedance amplifier in the front end of the current input, the impedance there is essentially zero. It's a virtual ground, so all the current is absorbed into the instrument quite nicely, and it doesn't produce any voltage at the input. So other than that, very straightforward. You can see the frequency over here. I'm not sure if this is actually focused here, but I think it is. This frequency over here matches exactly the frequency that is coming out of there. So that's pretty good, which means we are nice and set for our measurement there. So right now I'm actually doing some measurement. This is a live measurement, and the photodetector is running at 50 milliamps. And I'm taking the output here, and I'm also connecting it to the multimeter at the top there. You don't really need that. We can read this number over here. And I've configured the instrument such that the number that you see here is the actual magnitude between the two channels, and the number you see here is the phase. So I have some phase difference. It's going to measure the phase for me, and it's going to give me the absolute magnitude, so we don't have to worry about the phase between the two X and Y channels. We can get a magnitude response, which is exactly what we want, and I explained that earlier in the video. So it all looks very nice. Let's go ahead and try and see if it's actually measuring what we want. First thing first, let's block the light and see if this number goes down. And indeed, you can see that when I block the light, the number will slowly go down to 0. I have an integration of 3 seconds and a post time constant of 0.1 seconds, so it's going to obviously respond a little bit slower. And yeah, it looks good. So what does this number actually mean? Well, we have 264, remember this is an RMS, so we have 268 microvolts being measured, but we also have a gain of 10 to the 6 volts per amps, which means that we're measuring 272 times 10 to the minus 12. So 272 picoamps is what is being measured, which is in line with what we were measuring before. Of course, the intensity of the light is going to be less because we're chopping it, half the time. So there it is. So that looks pretty good. And let's go ahead and reduce the current. Actually, you know what? Before I do that, let me go ahead and turn the light off and see if it has any effect on the measurement. Now, you can also read the measurement up here. This is 5.4 volts. This is scaled, obviously, coming out of the instrument, but I'm going to use that because you won't be able to see anything when I turn the light off. The key is, will this change when I turn the light off, or is it completely independent of the ambient light? We go, turn the light off. There it is. You can see it has no change on it. Turn it back on. Beautiful. So the ambient has no effect on our measurement, which is exactly what we wanted to do. And if I go over here, and I move my hand around, I see no difference, and the measurement number here is very, very repeatable and constant. So let's go ahead and reduce the current to the photodetector even more. So right now we are at 50 milliamp. Let me go down to 20 milliamp, which was difficult to measure before. So when I go to 20 milliamp, obviously we have to change our scale because it's going to go down. So let's go and make the scale even smaller. Let's go to 5, no, even smaller than that. Now I'm in the nanovolt scale. That might be too much. There you go. We're sitting now at a 1 microvolt scale. That's not too bad. Let me change the integration a little bit more. Get a slightly more stable measurement. And there is that one limitation in this, and I'm going to tell you that at the end. So right now I'm measuring 0.784 microvolts. So it's 0.784 times 10 to the minus 12 amps. So it's a very, very small amount of current. I'm going to make it even smaller. Let's go ahead and make the current 10 milliamp. So let me show you that indeed we're dealing with 10 milliamp. There it is. You can see that we're getting 10 milliamp into the photodetector, into the laser diode, and it's settling down at 4.16 volts, right? So let's wait for this to settle down because I have an integration time of 10 seconds. And let's see what happens. So I should be able to make the scale smaller. Perhaps even smaller than that. Well, maybe not. Maybe let's keep it over here. There you go. So we're sitting around 230, 240 nanovolts. So which means we're measuring a current of 250 nanovolt times 10 to the minus 6. So this is 250 times 10 to the minus 15. So we're looking at attoamps now. So the current being produced by the LED is now in the attoamps range. But we can detect it no problem. Now, I can't even see the light, by the way. The light on the detector here, you cannot see it because it's too dim. And I can block it, though. I can put my phone in front of it, and the number should slowly go down. Let's see if it goes down. There it is. You can see that it is diminishing, which means we are definitely measuring current coming from the photodetector, and it's going to slowly go to 0. Remember, my integration time is very, very, very small, and I'm going to remove that, and it's going to slowly build back up again, and you can see that it's growing again. So even at these tiny, tiny numbers, remember we're talking about 250 times 10 to the minus 15 amps in the attoamps, but we are able to measure it, again, because of the lock-in capability. If I didn't have that, you would see nothing at all coming out, as you saw, even with a number larger than this, 10 milliamp, you could see nothing at all on the instrument. So this really makes a huge difference, and it's the only way to make this type of measurements. Now, there is a little bit of a limitation here, and the limitation has to do with the way I'm setting it up because I want to get everything on camera. The signal that's coming out of here, that signal is at the same frequency as the signal being detected here. And this runs over the case of the instrument, and these are fairly still close to each other. So any coupling through this to this cable and going into the input current of the lock-in amplifier is going to be detected as a signal of interest, even though it is not a signal of interest. So you have to keep these things far away from each other. You also don't want to put this really close to here because it's going to modulate ambient light also, and that's going to be into your measurements because we are talking about a tiny, tiny, tiny amount of current here. I mean, you can't even see the laser diode being on because it has such a small amount of current in it. But no problem in detecting this signal and being able to do this measurement. So there it is. And at the beginning, I'm sure something like this would have looked like magic. But now that you understand how it works, hopefully magic turns into knowledge. And I think that's really what science is all about. And I hope that you enjoyed this. These videos do take quite a long time to build and to set up and to make sure they work the way they're supposed to work. So if you enjoyed them, please let me know in the comment section. As always, Patreon supporters appreciate it. It's the reason why I could do this. It's the reason why I could buy this. So thank you to all my Patreon supporters. You're supporting everybody, of course, who can watch these videos and not just me. So I hope you like it. I'll see you in the comment section.